The bike alarm consists of two sensors connected to the GPIO ports of the Pearl Gecko. The Grove piezo vibration sensor uses piezoelectricity to generate a voltage from mechanical stress. When a vibration is detected, the sensor outputs a logic high. The Sunfounder active buzzer is active low. The buzzer is turned off when a logic high is sent through the signal wires. The software starts by initializing the LCD, the GPIO pins, and the cryo timer. Then the program enters energy mode 3. About every 2 seconds, the cryo timer wakes up and checks the state of the machine. If the state is in alarm mode and vibration is detected, it forces the GPIO pin to sound the alarm. The first iteration of the project stayed in EM0 the entire time. The device consistently drew 5 to 5.4 milliamps. With a standard CR2032 battery with 225 milliamp hour capacity, this device would have only lasted about 42 hours on battery. The next iteration of the project entered EM2 and used a sleep timer to wake up and check the state. Dropping the energy management down to level 2 improved the energy efficiency, but it still would have only lasted 68 to 81 hours on a charge. The final iteration used EM3 and used a cryo timer to wake the device. The device now would last for at least 128 hours and at most 500 hours. This was a significant improvement. Most people don't want to charge a device like this every couple of days. It was important to get the energy consumption to be as low as possible to make it more practical and convenient for the user. The stretch goals in my original project proposal were to connect the bike alarm to GPS so that a stolen bicycle could be tracked, and to connect the device to Wi-Fi to send me a message if the alarm had been activated. The GPS device another classmate let me borrow uses UART communication protocol to process a location. The device is normally used as a plug and play with other hardware, and there was no information about how to process the data from the device into a usable form. I found some Arduino libraries that I hope to copy the format from, but I ran out of time for this project. But maybe over the winter break I'll be able to get it working with an Arduino. Something else I tried that didn't work was using the vibration sensor itself as an interrupt. I thought I would be able to squeeze more energy efficiency out of the device if it stayed in EM3 until the vibration sensor woke it up. What I found was that the GPIO interrupt is activated on the rising or falling edge of a pulse, and so the signal needed to be fairly clean. The vibration sensor, on the other hand, was way too jumpy for the interrupt to acknowledge. I needed a way to debounce the vibration sensor like a flip-flop, and this would be a great starting place to improve the design going forward. Overall, I thought the project went well. My research skills have definitely improved from digging through unfamiliar documentation. I definitely feel less intimidated by a 2,000-page manual listing specifications for a device, which is a huge jump from where I was 3 months ago. It'll be interesting to build on what I've learned here in the years to come.